So good morning one and all. So let us start today's class. In the last class we have discussed about McCullough-Spitz neurons, or simply it is called as MP neuron. So we have seen how to represent Boolean functions using MP neuron, but it has got some limitations. So the limitations are: a single MP neuron can be used to represent Boolean functions which are linearly separable. So in the last class we have explained what is linearly separable. Okay, so we can able to draw a line or a surface which can separate a set of inputs which gives output as 0 or 1, something like this. Okay, so we have taken 4 Boolean points, and if I can able to draw a line something like this, so this line separates inputs which produce output 1, these 3, and this input produce output 0. So we can able to separate them. So then that is called linear separability. So using MP neuron, single layer MP neuron, we can represent only Boolean functions which are only linearly separable. So that is a drawback of MP neuron. So what about non-Boolean inputs? So we have taken inputs to be Booleans. What we have taken? The inputs belongs to either 0 or 1. So MP neuron can only deal with Boolean inputs. What if input is not Boolean? Some real values. Real values means input can be some value. Let us take 0.2 or 0.3, something like this. So if it is so, the MP neuron won't work. It works only with Boolean inputs. So do we always need to hand code the threshold? Yeah. So here the threshold theta is hand coded, right? We are calculating theta. So actually we need a mechanism to calculate theta, that is threshold. So here we hand code it. Hand code means we calculate ourselves. All inputs are equal. What if we want to assign more importance to some inputs? Yeah. So in this case we have taken all inputs to be equal. Suppose you take a simple OR gate, some theta here, x1, x2, x3. This is some decision y. Okay. Here we have taken all the inputs are given equal priority or equal importance. Okay. So what if you want to give more importance to certain inputs? Suppose we have taken a movie example. Okay. X1 is some kind of, let us take hero. X2 is the director. X3 is the rating. So in case of MP neuron, all these 3 inputs are given equal priority or equal importance. Okay. So what you have done, simply you have taken sum of all the inputs. Okay. So if it is more than theta, that is g of x. G of x is aggregation. If it is more than theta, we say output is 1. If it is less than theta, we say output is 0. Okay. So but sometimes, so I want to give more importance to a hero or heroine. Okay. Which means, so I want to watch the movie of a particular hero. I don't bother about a director and rating of the movie. I don't bother about remaining 2 inputs, x2, x3. They don't matter to me. What matters is hero or heroine. Okay. So that is not possible in MP neuron because all are given equal priority or importance. Okay. So we cannot assign a more importance to any input or less importance to any other input. All inputs are treated equally. Okay. So that is the drawback of MP neuron. Yeah. So as I told you just now, we can only deal with the functions which are linearly separable. So if they are not linearly separable, it won't work. Okay. These are the limitations of MP neuron. Correct? Yeah. So to overcome this, now we move on to the next model, that is called Perceptron Model. So that is a Perceptron model. Yeah. So the only difference is, in this case, each and every input has got a weight associated with it. W1 is the weight of input x1, W2 is the weight of input x2, W3 is the weight of input x3. So each and every input has got its own weight. Okay, so inputs are associated with some weight. So obviously, so we take decision based on the weighted sum, not some weighted sum. Okay, I'll explain what is weighted sum. Yeah. So let us take, this is the perceptron. What happens here? X1, the weight associated with x1 is W1, x2, W2, x3, W3, so on, so on, xn, Wn. Have n inputs and n weights. Now, so how to take decision? Based on the what? Based on the weighted sum, not some weighted sum. So what we do here? So here the aggregated, here we have two parts, right? So here this is the weighted sum, weighted sum. Now what happens here? So what is weighted sum? Input x1 into its weights W1 plus next input is x2, its weight is W2 plus so on plus last input is xn, its weight is Wn. Okay. Now if you write using a summation form, the weighted sum is I equal to 1 to n Wi into xi. This is the weighted sum. Obviously, how to take the decision? If it is more than or equal to theta, what do you say? Output is 1. The neuron will fire or the perceptron will fire. So if this is less than 0, less than theta, I equal to 1 to n xi Wi. If it is less than theta, output is 0. So this is the how the perceptron will work. This is the perceptron logic. So we are taking the weighted sum. Okay. Now here I am rewriting the above equation. What I am doing is I am taking theta inside the summation. I can take because it is independent of any subscript I. So this is the rewriting the above equation. Is it okay? I have taken theta inside the summation. So obviously this is greater than 0, this is less than 0. Okay. So what I have done is I have just taken this theta inside the summation. So if you take theta here minus theta, this becomes 0. Here minus theta, this becomes 0. Now this is the Now here, so we call something very important, something called bias. Omega naught that equal to minus theta is called bias. We denote omega naught with minus theta. So it's called bias. Okay. Now minus theta is nothing but omega naught. So you can also write this as minus theta as omega naught. So finally what we can write here is, what is the final equation? Output equal to 1 if the weighted sum, something like this, I equal to 1 to n omega I xi minus omega naught. So minus theta means omega naught, right? Okay, plus omega naught is greater than or equal to 0. Y equal to 0 if this is, I am not writing again and again, if this is less than 0. Okay. Now, so a more accepted convention is something like this. Okay. Here what I have done is I have taken next one input, that is x naught, that is always 1. Here I am adding an input x naught, that is always 1, and weight of x naught is omega naught, which is minus theta, W naught, that is minus theta. Is it okay? So the above equation can be written like this. Is it okay? What I am writing is, now what the weighted sum here? It just weighted sum is what? 1 into omega W naught, otherwise x naught into W naught plus x1 into w1 plus so on xn into wn. This is what we get, right? I am adding input x0 which is always 1, and with the weight of x0 is w0, that is always equal to minus theta. It is called bias. Now, so if you write this equation, what happens now? Summation I equal to 0 to n, because it is starting from 0, not 1. This is shown in red color, no? So in the previous one, I is starting from where? 1. But here I starts from 0, because so we are writing like this. So I can say xi wi greater than or equal to 0. If it is so, sorry, that is not theta, that is 0. If it is so, what do we say? If it is so, we say that output is 1, otherwise output is 0. If reverse happens, output is 0. Are you getting? So this is a more accepted convention for the perceptron model. Okay. Now, what else? Yeah. So what the main difference between a perceptron and MP neuron is what? Introduction of numerical weights for inputs and a mechanism for learning these weights. Okay. So the major difference between a perceptron and MP neuron is weights. In the MP neuron, there were no weights associated with inputs, but here we have a weight for all the inputs, and we have a mechanism to learn those weights. We have to learn these weights. Okay, I will come to this later, but the main difference is weights. Okay, next. Okay, so let us see how to implement a R function using a perceptron. We have seen how to implement R function, AND function, R function using a MP neuron, McCullough-Spitz neuron. Now let us see how to implement R function using a perceptron. Okay. Now please remember, in the perceptron, what is the basis? This is weighted sum, not sum, weighted sum. There is aggregated value. Okay. Now, so this is R logic. Correct? So 0 0 means 0. For remaining inputs, output is 1. Okay. What do you get? So you just, what is the logic? W0 into X0. I'm taking two inputs only, right? Okay. W1 into X1 plus W2 into X2. Anyway, X0 is always 1. Okay. The two inputs are X1 and X2. Okay. This is the logic. Simply. Here what is n value? N equal to 2. Two inputs. N equal to 2. Okay, right. Now here, okay, X0 is 1. Always 1. So we left with W0 plus, so W1 into X1 plus W2 into X2. Okay. So if it is greater than or equal to 0, the output is 1. If it is less than 0, output is 0. Okay. Now here, if input is 0 0, what is the output? 0, which means if both inputs are 0, if the both inputs are 0, output is 0, which means what? If inputs are 0 means x1 is 0 and x2 also 0. So W0 should be less than 0. Is it okay? I have written here. Second case, second row. X1 is 1, W0 is anyway always present. I think it is 1 0 1. Okay, third row. 0 1, output is 1, so it should be greater than 0. So W2 is more than minus W0 for the one more input, for the last input. Okay, let me write here otherwise. This is for first input. See, I am writing less than 0 here because the output is 0. Output 0 means the sum should be less than 0. Is it okay? So don't get confused with here. If output is 1, sum should be more than 0. If output is 0 means sum should be less than 0. That is the logic of the perceptron. Second input, what is the equation? Second input is 1, 0. Okay. So W0 plus W1 into X1, W1 plus W2 into X2, X2 is 0. So nothing will come here. It also should be greater than or equal to 0 because output is 1. So what do you say? W0, W1 is more than W0, more than or equal to W0. Third input, what is third input? 0, 1. So W0 is always present, W0 plus W1 into 0, 0, W2 more than or equal to 0. So what do you say? W2 is more than or equal to minus W0. Last input, both are 1. Both inputs are 1. Then what happens? W0 plus W1 plus W2 should be greater than or equal to 0 obviously. So so simply you can say W1 plus W2 should be more than or equal to minus W0. Now we have a system of inequalities. Okay. So if you solve them, you will get solutions. Okay. But you have so many solutions. One of the possible solutions is W0 equal to minus 1, W1 equal to 1.1, W2 equal to 1.1. Okay. So one possible solution is W0 equal to minus 1, W2 equal to 1.1, W2 equal to 1, both are 1.1, 1.1. Okay. Now, so what happens here? What is the line equation now? So basically here, this is the actual equation. Now what is solution? One of the possible solution is W0 equal to minus 1 plus 1.1 x1 plus 1.1 x2. Okay. This is a line. This is a boundary. I explained what is a boundary in the last class. So now what happens here? There is a boundary. Now this is a boundary. This is a line that is minus 1 plus 1.1. Otherwise, this is 1.1 x1 plus 1.1 x2 equal to 1. Okay. Now this line is a boundary which divides the 3 points. The 3 inputs lie on the above the line and one input lies below the line. Obviously, it's just like the MP neuron. It is dividing the entire space into 2 halves. So, and some inputs lie above it, some inputs lie below it. Okay. Now, as I told you, we have so many possible solutions. So, one among them is minus 1, 1.1, 1.1. So, here this line could be another solution. This red line could be one another solution. Okay, you may get so many solutions, so many possible solutions. Okay, so all these lines will divide the entire space into 2 halves. Okay, so some inputs lie on or above it, some inputs lie below it. So inputs which lie on or above it will produce output 1. Inputs which lie below it produce output 0. So that is a clear case. Okay. But the only thing is we get so many solutions, so many possibilities because we have a system of inequalities. Okay. So that is about perceptron. Correct. So we implemented OR gate using a perceptron. Yes. Now this is the difference between MP neuron and perceptron. In MP neuron we take only sum of inputs. That is called aggregation. But here we have a weighted sum of inputs. Okay, I have shown the weights in red color. That's the difference between MP neuron and perceptron. Basically, the main difference is weights. Yeah, even a perceptron separates input space into 2 halves. All inputs which produce a one lie on the one side of other lines on the other side. Yeah, one more thing is a single perceptron can only be used to implement linearly separable functions. Here also using single perceptron, you can implement functions which are linearly separable. That is a drawback of the MP neuron, but drawback of perceptron. But the advantage is, so you can overcome remaining advantages of MP neuron. What are they? Inputs need not be real. We can give importance to some inputs. Okay, all those things. But anyway, it also applicable to a linearly separable functions. Right? Now, before proceeding further, so let us discuss about errors. Now, there are possibilities of errors, obviously. Okay, let us fix the threshold W not equal to minus 1 or minus W not equal to 1 and try different values of W1 and W2. Say W1 equal to minus 1, W2 equal to minus 1. Okay. So what they want to say is, so we want to, as I told you, we have a system of inequalities, right? So we get so many possibilities for these weights W0, W1, W2 for 2 input OR gate. Okay. So we can choose them arbitrarily, correct? So let us fix without using generally W0 equal to minus 1. Okay, that is fixed. Now what about remaining? I am saying W1, W2 both are minus 1. So W1 equal to W1, W2 both are equal to minus 1. Now what happens to the geometric interpretation? Let us go into it. So what is the line now? What is the line equation? Actually line is W0 plus W1 x1 plus W2 x2 equal to 0. This is the line. This is the boundary. Suppose in this case all are minus 1s. Minus 1 minus x1 minus x2 equal to 0. Now the line is x1 plus x2 plus 1 equal to 0. This is the line. This is a separating line. So if you draw the line for this geometry, it is somewhere here. Okay. So what happened here? All the inputs lie above the line. Okay. According to the logic, what should happen? If all the inputs lie above the line, what should happen? What happened here? Line is somewhere here. This is the line. All our inputs lie above the line. Okay, which means according to decision rule, all inputs will produce output as 1. That's the meaning. But in OR gate, what happens? In OR gate, only 3 inputs produce output 1. One set of inputs produce output 0. How many errors are there? How many errors are there? This is an error. What is error? This is error because 0 0 produces 0 output. It should be below the line somewhere here. So this is an error. Remaining are correct, but the 0 0 origin is an error because it produces 0 output, but it lies above the line. It should have been below the line. Okay, that is error. One error. Okay, we are getting errors. Suppose I choose some other values. Okay, so let us choose some other values. 1.50. W1 is 1.5, W2 is 0. 1.50 means 1.50 means what? Minus 1 plus 1.5 x1 equal to 0. Is it so? W1 is 1.5, W2 is 0. So which means x1 equal to some line. Where is that line? This line, vertical line. So 1.5 x1 equal to 1. x1 equal to 1.5 by 2. 2 by 3, some line. Okay, again what is the problem with this line? Line is vertical line. Somewhere here. Okay, line is something like this. Where are the inputs? Again, how many errors are there? How many errors are there? So this lies below the line. Remaining should lie above the line. It should be above the line because it is producing output 1. What is this? 0, 1. This is 1, 0. This is 1, 1. This is 0, 0. So these three should be above the line or one side of the line because they produce output 1. It should be on other side of the line because it produces 0 output. So again this is an error. It is in the error. Okay, are you with me or not? Okay, again one error. So last case is 0.45, 0.45. What is the line? 0.45, 0.45. What do you get? What is the line you get? -1 plus 0.45x1 plus 0.45x2 equal to 0. Where is the line? This line. This line. Okay. So there you are getting 3 errors. Is it okay? Now you can, in this way you can find out the number of errors depending upon the values of the weights. In the table I have mentioned all the errors. So depending upon the values of W1, W2 we are getting some errors. But ideally we wish to have 0 errors. Okay. So we try to get a minimum errors. Ideally we hope for 0 errors. Okay. But when it is possible to get 0 errors. Okay. So for each analysis we keep W0 equal to fixed, that is -1, and plot the error for different values of W1, W2. Okay, just now we have done it. Now this is the equation we are looking for. Okay. Now when do we get errors? This is very, very important. In our function, when do we get errors? Suppose if both inputs are 0, okay, output should be 0. So if output is 1, we get errors. Okay, this is one possibility of error. If both inputs are 0, if output is 1, that is a possibility. Otherwise, outputs are equal. Okay, when both are 0, if output is 1, then we get error. Otherwise, if both are not equal, both are not equal to 0, remaining 3 cases 0, 1, 1, 0, 1, 1. In these 3 cases, output is 0, we get errors. Okay, what I want to say is, let us write this. If x1, x2 equal to 0, 0, but the output is 1. Output is 1. When the output is 1, please remember, what is the condition? W0 plus W1 x1 plus W2 x2 is greater than or equal to 0. This is a condition for getting one output. If x1, x2 equal to 0, 0, but this is true, then what happens? You get errors. Or what another possibility? Or x1, x2 not equal to 0, 0. Here they are not equal to 0. Both are not equal to 0. x1, x2 both are not equal to 0. Which means they can be 0, 0, they can be 1, 0 or 0, 1, 1, 1. Any one of the 3 cases. And in this case output is 0. When the output is 0, W0 plus minus W0 plus W1 x1 plus W2 x2 is less than 0. Okay, so this is a condition for getting an error in case of OR function. Okay, anyway, so depending upon the values of weights, we may get errors. I have written in the table some of the possible errors. Okay, now here, so we have taken a error surface. Okay, now here, So this is W2. I have taken minus 4 to 4. This is W1. This is also minus 4 to 4. So in our example, whenever W1 is 1.1, 1.1, W1 is 1.1, W is 1.1, we are getting 0 errors. It is classifying the points correctly. The classification is proper. Classification means dividing the points. So which means in this example, so 1.1 may be somewhere here. W2, W1, 1.1 may be somewhere here. Okay. So this dark green indicates very less errors. You may get 0 errors, maybe 0.5 errors. Error probability. Okay. Now, so this region may indicate, this light green, light blue indicates more errors. This indicates large errors. How many? 4. Okay. So this is a brief way of identifying the error surface depending upon the W1, W2 values. So if you choose proper values for W1 and W2, you may get 0 errors. If not so, we may get more errors. So this is a brief way of illustrating the error surface for W1 and W2. So we have shown all the errors using different colors. Green, light blue means very less errors. Red means more errors. In the same way, we have shown some other colors also. They indicate in those regions you may get more errors, something like that. Okay. So that is about getting errors in the perceptron model. Okay. So that is about perceptron we have seen. Yeah. So we stop here. Thank you.